Okay, Section 8, Part B, continuing our idea of the binomial distribution. To recap, if we have a fixed number of observations, we know how many times we're going to do something or pick something. Each time we pick, it's either a success or a failure. It meets a condition or it doesn't meet a condition. And the probability of a success is the same every time we pick, regardless of what we picked before, the independence. Then, if you're talking about the number of successes you actually get, then its pattern of randomness, its probability distribution, is called the binomial distribution, abbreviated capital B and P. We looked at some examples, and we saw that for samples, we did some of these without calling them by this name back in Section 5, for samples of sizes 1, 2, 3, and up to 4 even. Beyond that, they start to get pretty complicated to work out. So computing these binomial distributions can be very complicated. You either use software or you use tables. Even for software, these calculations involve factorials. So even for software, factorials get messy really, really quickly. You'll know what I mean if you have a way of typing 2000 factorial into your calculator. If you happen to have a factorial button, where is it? Here it is. I'm reasonably sure this is not going to like 2000 factorial. No, it's just way too much for it. So for actual sample sizes that you're going to see in the real world, these binomial techniques, the fact that it is a binomial distribution, and it is not very helpful for a very large sample. They're very, very complicated to compute. Even software will have its limitations. Tables generally don't go up much past 20 or 30, and we don't generally do samples that small. So in the end, although these examples that we've been looking at, the example we've been following here is picking a sample of people from the population of the United States, pick 2,500 people, simple random sample, and ask them whether they like action movies. Well, try 2,500 factorial on your calculator and watch it laugh at you. You're just not going to be able to deal with that as a binomial distribution. The number of yeses that you get in this scenario is a binomial variable, n being 2,500, p being 0.6 if that was the proportion of yeses out there. But again, it's not very helpful because even software is going to have a problem with computing binomial distributions like that. So although it is a binomial distribution and can theoretically be computed as such, only theoretically, in practice it's way too complicated. On the other hand, we've also seen that as samples get larger, things begin to become not only very predictable, but very familiar as well. Everything that we did in Section 7 alludes to this, right? Given that 60% of people in the United States would say yes, they like action movies, if you pick a very large sample, probably you're going to get close to 60% of the sample saying yes. Large sample, less variability. You see, you put the two ideas that we talked about in Section 7 together, right? The fact that it's a simple random sample means that whatever the proportion of yeses are, it should be bouncing around, centered at, sample to sample to sample to sample to sample, centered at 0.6. That's the lack of bias. A simple random sample makes bias impossible. So it should be centered at 0.6. And the fact that this is very large tells you that it's not going to vary that much from sample to sample to sample. So they're tightly clustered around 0.6. So of all the samples you could do, most of them are going to be pretty close in there to 0.6. Say the same thing another way. There's a high probability that the sample you do will be very close to the truth. So that's just putting a little math behind what we know in the first place, right? If 60% of people like action movies, and we're not cheating this process by Chuck Norris and all that, if 60% of people out there like action movies, then if you ask a lot of people, probably about 60% of them will say yes. It's common sense. It follows from everything we did in Section 7. But the reality is there are no guarantees. However, the fact that probably about 60% of them will say yes for a large sample, or if you prefer, there's a high probability that very close to 60% of them will say yes, or if you prefer, the vast majority of samples will result in something very close to 60% saying yes. Any of those things is just saying what we said in the first place, right? That large samples are very predictable. You ask 5 people, you might get anything, but if you ask 5,000 people, you'll very, very probably get something very, very close to the truth. Put it all together, and that means that large samples are very predictable. Small samples bounce around a lot using these probability rules, but the probability rules for large samples are so stable that things are very, very predictable. However, whether the sample is large or small, we are talking about a random variable. You do something random, you pick or do something n times, and you get a number from that. Whether it's x, the number of successes, or p hat, the proportion of successes. Whether it's the number of successes or whether it's p hat, which is x divided by n, the proportion of successes. Again, notice that it's just a unit change, right? To go from count to proportion, you divide by n, the sample size. To go back the other way, from proportion to count, you multiply by n, the sample size. Notice number 1, that that's a unit change. Notice number 2, that it's the nice kind of unit change. It was the shift. It was adding numbers to everybody that was a little bit tricky. And notice number 3, that when we talk about the mean and standard deviation from section 6, if we do a unit change, if we multiply every possibility by a number, whether it's 2,500 or 1 over 2,500, when we multiply or divide everybody by a number, then we multiply or divide the mean and the standard deviation by that number. Again, it's shifts that are a little tricky, but multiply-divide unit change has the obvious effect on both mean and standard deviation. All this means that if you, like I said in the last video, that if you understand one perspective, you understand the other. So with all that in mind, let's talk about the mean. We've talked about the shape of this probability distribution, binomial, and this one's just a unit change away. So let's talk about the mean and standard deviation of these random variables. Now, before I do this, bear in mind that these could theoretically, only just, these could theoretically be computed the long way, right? Let's take an example of one that we have looked at. 20% of people have blue eyes, so if you pick 4 people, then here in chart form or in picture form are the probabilities of 0, 1, 2, or 3 people having blue eyes. So then you can compute the mean and standard deviation of this random variable in the old section 5 sense, right? Mean is 0 times the probability of 0 plus 1 times the probability of 1 plus 2 times the probability of 2 plus 3 times the probability of 3. Let me just type that in really fast. 0 times 512 plus 1 times 0.384 plus 2 times 096 plus 3 times 098. Keystroke, 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 0.6. Seriously though, you see there's a shortcut here. And that's what it is. It's a shortcut. It's important to understand when we talk about the formula we're about to talk about. It's the same answer you would get by doing this times this, plus this times this, plus this times this, plus this times this. Mu is 0.6. And the standard deviation, for what it's worth, keystroke, 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 is 0.6928 something it looks like. So obviously I'm using a shortcut when I find the mean and standard deviation of this binomial random variable. Now let me stress, if it's not a binomial random variable, if it's any of the other examples that we looked at, A couple plans to have children until they get a boy or 3 girls, whichever comes first, or the racehorse example. Those were not binomial random variables. So for those charts, we have no shortcuts. Likewise, for the other examples that you didn't even have to compute in the first place, where they just gave you the charts, whether it was the chart for Keno. Let's see, do I have that below? Not really. So the Keno was, what was a 1/4 chance that you're going to win $3 and a 3/4 chance that you were going to win nothing, something like that. Or the card in the deck, which was a little more complicated, I might have that, yes. So in the case of the card from the deck, red card you win nothing, spade you win $5, club you win $10, ace of clubs you win a total of $30. So here it is. So half the cards will win you nothing, a quarter of the cards will win you $5, 12 of the 52 clubs will win you $10, and 1 of the 52 clubs will win you a total of $30. So in so many words, they're just giving you the chart. It's a generic random variable, but there's nothing binomial about it. So there's no shortcut. 0 times that, 5 times that, 10 times that, 30 times that is the mean, and likewise the various steps that you go through to find the standard deviation. So we don't always have a shortcut, but if it is a binomial random variable, if you're in this situation where you meet these 4 conditions, you know, hang on a second. If it's this situation where you meet these 4 conditions, you know how many times you're going to do something. Every time you pick, it's a success or a failure. The probability of success is always the same, and you're talking about the number of successes. If you meet those conditions, then it's a binomial random variable, and we have some shortcuts. Again, it is a shortcut, so it is the same answer you would get doing things the other way. It's just that you don't have to do them the other way. This can either be a minor time saver. Let's just talk about the mean for a second. This can either be a minor time saver in the case of using our shortcut instead of doing 0 times this, plus 1 times this, plus 2 times this, plus 3 times this, plus 4 times this. Or it could be a major time saver if you had 81 columns to deal with. And now bear in mind, it's the large samples that are ultimately of interest to us, right? So you can see how this shortcut could save you an awful lot of work. And here it is. Draw a simple random sample of size n from a large population. Well, populations are large. Large enough so that they're not going to miss n of them. N can be very large, 5,000 people. But when you're picking from hundreds of millions of people or billions of people, right? So n can be very large, but on its worst day, it's never going to take any noticeable bite out of populations. Populations are always lots more than we have to pick, than we can actually pick. Draw a simple random sample of size n from a large population. Well, populations are large, with proportion p of successes. Now again, I've said this in a way that's handy for the future, but remember, some populations are more theoretical than others. You can pick 2,500 people from hundreds of millions who may or may not like action movies, and 60% of them do, p is 0.6. Or you can pick 100 flips of the coin from the population of all possible flips of the coin, and the probability of a head is 0.5, right? So some populations are a little more theoretical than others, but that's okay. Whether it's hundreds of millions or a theoretically infinite number of possible flips of a coin, it's still a lot more than we're ever going to pick or do. So this is just a recap. Let x be the number of successes. Let x be the number of successes. Let p hat be the proportion of successes in the sample. So x is the number of successes you actually get, statistic. P hat, which is x divided by n, is the proportion of successes in the sample proportion. then everything I've just said tells you that x is either binomial n comma p. Flip a coin 100 times. Fair coin, probability of a head is a half. Always probability of a half. X is number of heads. Exactly binomial. Or it could be approximately binomial because you're technically picking from a finite population, right? Like 2,500 people from hundreds of millions. Again, the population of the United States is not going to miss 2,500 people vis-a-vis whether they like action movies or not. So it's effectively binomial. With replacement, without replacement, it doesn't make any difference when what you're picking from is so much bigger than what you're picking. So in the real world, that magical thing called close enough, like picking 2-3 cards out of hundreds of cards, right? So for these random variables, and now bear in mind, one is a unit change of the other. Divide by n to go the one way, multiply by n to go the other, but they're just the same basic phenomenon measured in two different ways. Number of successes, proportion of successes. X can be 0 or 1 or 2 or 3 or 4 or up to n. P hat can be 0 over n or 1 over n or 2 over n or n over n. So X can be however many things between 0 and n. P hat can be lots of things between 0 and 1. And for a large sample, it's effectively anything between them. But large or not, whether it's a sample of size 2 or a sample of size 2 million, we've got the following rules. For these random variables, the mean of x is n times p. This, I think, is common sense, right? We'll do some examples in a second, but if you think about the way this formula plays out, the means are going to be common sense, and as usual, the standard deviations you don't have a lot of instinct for. So the mean, when you're in this binomial situation, the mean of the variable is n times p, and the standard and the mean of the proportion is just plain old p. Standard deviation, remember, is average distance from that center. You don't have an awful lot of instinct for. But for the count, it's the square root of n times p times 1 minus p. That is, n times p times 1 minus p, square root the whole thing. And for the standard deviation, for the proportion, sample proportion, it's p times 1 minus p over n, square rooted. Now again, this can be an actual population, all the people in New York State. You pick 2,500 people, and you're picking approximately nothing from New York State, so we've got the independents. Or the theoretical population of all possible coin flips, etc. This, again, is an artificial distinction. You'll go a long way with these ideas if you think of flipping a coin 50 times as picking 50 flips from the population of all possible flips. It's a distinction without a difference. What to notice? Well, ultimately, the counts formulas are a little easier to deal with because the numbers are not so microscopic. But like I hinted in the last video, the proportion is the handy perspective for the long run. These are the formulas that you're going to get sick of seeing. These are the formulas that are with us for the duration. Counts, well, easier in the short run because the numbers aren't so small, are less handy in the long run because to compare things, you've got to divide by the total anyway. So let's look at Formula 3 and Formula 4. Let's focus on the practical statistic, proportion of successes in the sample. You're picking from a population where 50% of all possible tosses of the coin land heads. You could get any proportion of heads when you do it so many times, but it's bouncing around 50%, right? You're picking from a population where 10% of people are left-handed. You might get any proportion of left-handed people in your sample, but in terms of its randomness, you're bouncing around 10%. You see? It's the logical center of the randomness. Now let's think about that again. This is a random variable. It might be pretty much anything between 0 and 1. Well, if n is large, lots of things between 0 and 1. If n is 4, 5 different things between 0 and 1. But it could be anything between 0% successes and 100% successes, right? 0 to 1. But it is a simple random sample, right? And a simple random sample eliminates the possibility of bias. Apart from the word games that we play with things, if your parameter really is what you're claiming it is, a simple random sample eliminates the possibility of bias. So what are we saying with this formula? Remember, p hat is the statistic. It is the arrow from the bow. It is what we're estimating with. And p is the target. It is what we're estimating. Proportion of people you pick who are left-handed. Proportion of everybody out there who's left-handed. It's important to remember, in the real world we don't know p, but we're not in the real world yet. We're still, as I said, in these sections, presuming that we know the rules, the governing principles, the underlying realities. And the sample is still in our future. So when you pick from a population where p is the proportion of successes out there, you might get anything. P hat might be 0, might be 1, might be anything, but sample to sample to sample to sample to sample, it's bouncing around what it's aiming for, right? The logical center of the randomness of the thing you're estimating with is the thing you're estimating. Let me blow that up and say it again. The logical center of the randomness of the thing you're estimating with, try it again, the logical center of the randomness of the thing you're estimating with is the thing you're estimating. In other words, his randomness, sample to sample to sample, or what the sample is likely to be in probability terms, is bouncing around what you're aiming at. So in the end, this is just putting a little math and symbol behind the principle that we talked about in the first place. The center of the randomness is what you're aiming for. That, remember, is what we meant by no bias. When the logical center of the randomness is centered, it is what you're aiming for. So in the end, we're just saying what we said in section 7. A simple random sample means that it's impossible to have any bias. P hat might be anything, but sample to sample to sample, or in probability terms, it's bouncing around what it's centered at. It's bouncing around what it's aiming for. It's centered at, its randomness is centered at what it's aiming for. Let's take a look at Formula 4. The thing to notice about Formula 4 is that if we divide by n, it's not going to let me highlight that root per se, is it? But we're dividing by n, right? So all other things being equal, let's say you know p. All other things being equal, if you pick more and more and more, if your sample size is bigger and bigger and bigger. Now again, it's never so big that you lose the independence. It's never so big that you're asking 10% of the people in the world. We never get near that point. Populations are too large to deal with. 5% of them are too much to deal with. So with that understanding that it never gets so big that it takes a bite out of what you're picking from, as the sample size gets bigger and bigger and bigger and bigger and bigger, then you're dividing by more, right? And that will make this number smaller. You know, if this is 5, then the number's not going to be all that small. But if this is 5,000, then this thing is going to be very small. So the larger n is, the smaller this thing is. What is this thing? Standard deviation measures spread. Standard deviation measures variability of this statistic. The proportion of successes you get when you pick n of them. Might be 0, might be 1, might be anything in between. But sample to sample to sample to sample to sample, how much are they varying? How spread out are they? That is always what standard deviation measures. The thing that measures how much the statistic varies from one sample to another, or if you like, the thing that measures how the statistic varies in probability terms, what it's likely to be. Remember, the one is exactly what we mean by the other. The thing that measures how the statistic varies from sample to sample to sample. The thing that measures how the statistic is likely to, how the statistic varies in probability terms. How likely one sample is to be close to the next sample, or how likely you are to get different answers. The thing that measures how much the statistic varies gets very small if n is large. So this, number four, is just putting a little math behind the other principle from section 7. Large sample, less variability. Math. Large sample, n is larger, number that measures how much the statistic varies is smaller. Which I'm sure is exactly what I'm saying down here in my notes, right? There you go. I think I need to shrink this a little more. There you go. So let's take some examples. So up here I'm just recapping. Example 1. Maybe I can blow this up a little more. Example 1. A fair coin is flipped 100 times. So now we're talking about number of, these should be capital X's, by the way, so sorry about that. A fair coin is flipped 100 times. We're talking about number or proportion of heads. So the probability of a head is a half. Let X be the number of heads that you get when you flip a coin 100 times, the left-hand side. Let B hat be the proportion of heads that you get when you flip a coin 100 times. X can be 0 or 1 or 2 or 3 or 99 or 100. P hat can be 0 or 1 over 100 or 2 over 100 or 99 over 100 or 100 over 100. 0 to 1. So these principles should be pretty much common sense, right? If you flip a coin 100 times, a fair coin, 100 times, you might get any number of heads. They might all be heads, they might none of them be heads. X could be 0, X could be 100. But you're going to be sample to sample to sample. You're bouncing around 50 heads, right? N times P. Now, sample to sample to sample, pick 100, do 100 coin flips, what proportion of heads do you get? Do 100 coin flips, what proportion of heads do you get? So on and so on and so on. P hat could be 0, could be 1, but sample to sample to sample, of course, it's bouncing around that original 50%, 0.5, right? So these principles, number 1 and number 2, are very common sense. As always, means tend to be very intuitive. Standard deviations are very weird. Okay, given that in a sample of 100, what you're likely to get, the number of heads you're likely to get is bouncing around 50. How much more or less than 50 is it on a good day? On average, your average sample of 100 coin flips is how much more or less than 50? Because you're not going to get it on the nose, right? If you flip a fair coin 1,000,000 times, you're almost certainly not going to get 500,000 heads, right? So for large samples in particular, you're highly unlikely, individual bars are negligible, so you're highly unlikely to get it on the nose. If I say that you flip a fair coin 1,000,000 times and you're probably going to get about 500,000 heads, well, about 500,000 covers a lot of territory, right? A lot of bars. So on average, how much more, that's what standard deviation measures, remember, average distance from the center. On average, how much more or less than 50 flips are you likely to be? You're bouncing around 50. On a good day, how much more or less than 50 are you likely to be? Of course, if you flip a fair coin 100 times, it's highly unlikely you're going to get 10 heads, right? 49 wouldn't really surprise you, but 10 would be a little weird. So, average distance from the center, as always, just as important as what you're bouncing around is how far away from it you tend to bounce. Remember, the average person has one ovary. The typical person does not. The average person has one ovary, give or take one ovary, literally 0 or 2. So the standard deviation, the average distance from the center, is just as important as the mean. Only it's a little less obvious what the answer is. It's the square root of 100 times 0.5 times 1 minus 0.5, which it works out to 5 exactly. Usually this is going to be irrational because of the square root. A couple of the examples I have, it turns out to be nice. So there you go. When you flip 100 coins, fair coins, you're bouncing around 50 heads, give or take 5, right? So standard deviation can always be thought of as average distance from the center, loosely speaking, how far from the center you're likely to be, or, territory on a good day, right? So 45, 5 under, 5 above, 45 to 55 heads wouldn't really surprise me. The further away you get from that, you're straying into weird territory, right? We'll be more specific when we bring the normal stuff into this a bit later. But in any scenario, standard deviation represents the average distance from the center. 50 flips, give or take 5. 45 to 55 heads, probably. What about the standard deviation perspective? Well, the proportion perspective over here on the right. The proportion of heads is bouncing around 0.5, because of course it is. Standard deviation is 0.5 times the other 0.5 divided by n, which is 0.05. So there you go. Same statement, different perspective. When you flip a fair coin 100 times, you're bouncing around 0.5 heads, give or take 0.05. Bouncing around 50% heads, give or take 5%. 0.45 to 0.55 proportion of heads. 0.5 minus 0.5, 0.5 plus 0.5, on a good day. So 0.45 proportion of heads, 0.55 proportion of heads, anything in between wouldn't really surprise me. But you get more than one standard deviation away from the mean, and you're getting into weird territory, right? By the way, notice that this is 100 times smaller than this, and this is 100 times smaller than this. Remember, multiplying or dividing by n, that kind of unit change from section 6, has the obvious effect on the mean and the obvious effect on standard deviation. These are just unit changes away from one another. So if you multiply or divide by n, if you do that kind of unit change, left to right, divide by n, right to left, multiply by n, then it has the obvious effect on mean and the obvious effect on standard deviation. 50, divide by 100, which is n, you get the 0.5. 5, divide by 100, which is n, you get the 0.05. Or the other way, right to left, multiply by n. P hat turns into x by multiplying by 100. 0.5 turns into 50 by multiplying by 100. 0.05 turns into 5 by multiplying by 100. However you slice it, these numbers are n times smaller than their counterparts over here. Divide by n, you go from this number on the left to the number on the right. Multiply by n, you go from the number on the right to the number on the left. That should be obvious on the top, right? This divided by n is going to be p. This multiplied by n is going to be, well, what can I tell you? N times p. But it's a little less obvious down here because of the root, right? Now this works better on a chalkboard, but I didn't plan that far ahead. If you divide this by n, that's the same as under the root dividing by n squared. And then one of the n's cancels. So because of the root, instead of going away, it goes to the bottom. But sure enough, algebraically, if you divide this by n, you will get this. And if you multiply this by n, you will get this. And the relationship here proves it, because the one is obviously 100 multiplied or divided to get the other, right? Example 2. A fair die rolled 2,000 times, and let x and p hat be the count and proportion of some particular number, let's say 1. Now again, The fact that it is a 1 is irrelevant. It might as well be 6 different colors on the cube, right? Proportion, count the number of red sides that come up, the number of ones, or the number of whatever symbol you put on that particular side of the die, a circle, a star, whatever. The fact that it is a number is irrelevant, right? Our perspective is the categorical. You get a 1, you do not get a 1. Categories. So over here we've got the mean and standard deviation of the number of ones. What the number of ones on 2,000 rolls is bouncing around, and how far away from that guy it tends to bounce. And over here, same ideas for proportion. So of course 2,000 rolls, and the probability of 1 on a fair die is a sixth. So n times p. 2,000 times a sixth, 33 and a third. 333 and a third. 0.3 repeating, of course. I'll round to 2 places. I'll round to whatever I feel like here. But, 333.3 repeating, basically. Call it 333 just for verbal purposes. Well, first of all, notice that it's, we talked about this, expected value. It's not expected and it's not a value. This is not something that the die could land. It'll land one or two. This is not a number of ones you could have, right? But the randomness is what it is. If it's not a whole number, that's okay. It's simply what you're bouncing around. So again, exactly anything on 2,000 rolls is pretty negligible. So you would never want to say anything like, if you roll the fair die 2,000 times, you'll probably get 333 ones. Nothing could be further from the truth. Probably about 1/6 of them being ones just covers too much territory on a large sample. But, the actual things you could get, number of ones, whole numbers, the most likely possibilities are in this general vicinity, right? This is where the probability peaks out, more or less. It's certainly the balance point. Now, I should point out, if things are very asymmetrical, as we've seen in the past, where it peaks out and where it balances are not necessarily the same. But in these scenarios, they're probably not very far away from one another either. So it balances at 333-ish ones. Might be more than that, might be less than that, but sample to sample to sample. 2,000 rolls, 2,000 rolls, 2,000 rolls, 2,000 rolls, 2,000 rolls. Count the ones, count the ones, count the ones, count the ones, count the ones. It's bouncing around 333-ish ones, right? Now, obviously, it's not going to be dead on 333.3 repeating ONES's, right? That literally makes no sense. So how much more or less on a good day do you tend to be from 333.3 repeating ones? Well, that's the standard deviation. Average distance from the center. On average, in an average sample of 2,000 rolls, how much more or less than this highlighted number are you going to be? So square root of n times p times 1 minus p. Without losing any accuracy there, suffice to say that it's 2,000 times 5 divided by 36 and then square root. 16.6 repeating. So just for verbal purposes, let's call it 17. So on average, you tend to be, the number of ones you get when you roll the die 2,000 times tends to be 17-ish more or less than 333, right? So 333 minus 17 wouldn't really surprise me. 333 plus 17 wouldn't really surprise me. But the further away you get from that, you're getting into unlikely territory. More than one standard deviation away from the mean, and you're getting into very unlikely territory. Remember the court case we talked about, Castaneda v. Pacheda, if I remember right. What about the proportion perspective? Well, if you flip a lot of coins, then if you roll a lot of dice, then the proportion of ones, of course, is bouncing around a sixth. P itself. But what is a sixth? 0.166666666. somewhat coincidentally with number 2, we can ignore that, but 0.166666. But how much more or less than 1/6? How much more or less than 0.166666 is the proportion of 1s likely to be? Well, n times p, p times 1 minus p divided by n square rooted, and that's about 0.00833. I'm pretty sure that was 2 zeros. Let me just double check that. 5/36 divided by 2000. Take the square root, some scientific notation there. Yeah, sure enough, 0.0083333 repeating. Well, in a word, small, right? I mean, what's the takeaway from this highlighted number? It's 0.00 something. It's less than 1%. If percent is a little less confusing, oh, and by the way, the last thing we need is a third perspective on all this, right? But the percent of successes would be p hat times 100, right? And much the same kind of thing would apply. I'm just going to verbally go to percent. As a general rule, percents are a nice way to say things. They're nice ways to state questions. They're a nice way to leave answers. But for formal calculations, always do things in terms of proportions, decimals, out of 1. And it'll be one less thing to worry about. One more set of formulas we do not need. So I'll say it verbally as percents, but they're really proportions and they're out of 1s. So 0.1666 repeating is a 1/6. So we're bouncing around, say, 17-ish% 1s in our sample. Give or take, well, less than 1%, right? 0.8%. So, in a word, small, right? No bias. 2,000 rolls of the die you're about to do are philosophically interchangeable with any other 2,000 rolls of the die you're likely to do. There's no possibility of bias. So you're centered at what you're aiming for. Remember, this is the probability of a 1, which for a die in the real world we're never going to know. But if you roll it 2,000 times and get about 1/6 1s, that's pretty good prima facie evidence that it's a fair die, right? Or at least that the probability of a 1 is what it's supposed to be. But how much more or less than 1/6 1s is your typical sample of size 2,000 going to be? Well, in a word, small. You roll a fair die 2,000 times, you'll very, very probably get very, very close to 1/6 1s. That is to say, you're bouncing around 1/6 1s, and the thing that measures how far away you're likely to be is very small. Right? Many, probably, about. Well, the many we've wrapped our mind around, the about we've kind of wrapped our mind around, and the probably remains to be seen. Now again, the thing to notice here is that this number is very small. Remember, on its worst day, p hat is between 0 and 1, and it centers around 0.00, it centers around 0 point something, right? And on its worst day, it's back there at 0 or up there at 1. So the thing that measures how much variation there is in something that on its worst day can only be between 0 and 1, and something which is going to not vary all that much if n is very big, the thing that measures its variation is, in a word, small, right? You know, typically it's 0.0 something, right? Even if it's only 100, typically it's 0.0 something. So these do tend to be very small. As always, when you're dealing with very small numbers, watch your rounding. If we're content to compute this thing, then it doesn't really matter too much how we round it. But of course, we're computing it to use. How we use it remains to be seen. But it's common sense that whenever you're going to use something, you don't want to round it too much. So if I were going to use it, I'd probably keep about this much accuracy here. I probably would keep a little bit more accuracy over here. Example 3. Pick 400 people from a population where 10% are left-handed. So n is 400, p is 0.1. A success is being left-handed. Population, so the 400 doesn't make a dent in it. Independence, all of that. X is the number of the 400 people who are left-handed. P hat is the proportion of the 400 people that are left-handed. X is 0 or 1 or 2 or 3 or 399 or 400. P hat is hundreds of different things between 0 and 1. Effectively anything between 0 and 1. But obviously, if you pick 400 people from a population where 10% of them are left-handed, probably about 10% of the ones you pick will be left-handed, right? And that's exactly what this formula is saying. The randomness is centered at 40. When you pick 400 people, you might get more than 40 left-handed people, you might get less than 40 left-handed people, but that's where the probability is centered. Sample to sample to sample of size 400, you're bouncing around 40 left-handed people, and you're bouncing around 10% left-handed people, 0.1 proportion. Very common sense, right? Now your typical sample of 400 people, how much more or less than 40 left-handed people are you likely to get? Standard deviation. Square root of n times p times 1 minus p. Square root of 400 times 0.1 times 0.9. Let me just do that out. 400 times 0.1 times 0.9 is 36. And then the square root of that is exactly 6. These don't generally tend to be nice. That was a bit of a coincidence. So there you go. On your average sample, you'll get 40 left-handed people, give or take 6, right? 32 wouldn't surprise me. 46 wouldn't surprise me. The further away you get, it starts to get a little surprising, a little weird. Now, look at where we're going with all this. You know, if you picked 400 people from a population where you're told 10% of them are left-handed, and you got 43 left-handed people, it wouldn't really bother you. But if you got, let's say, 100 left-handed people, or 200 left-handed people, that would kind of bother you, right? What would be your reaction if you were told 10% of people were left-handed, you pick 400, and half of them, 200, are left-handed? Well, you can see that what we've just been saying says that it would be a very weird sample, and sometimes you get very weird samples. So where does that leave you? If you pick 400 people from a population where you're told that 10% are left-handed, and you get 200 left-handed people, then logically you can conclude one of two things is going on. Number one, through sheer randomness, you happen to get a cosmically unusual sample, and we'll look at how unusual in future sections. And that's certainly possible. Sometimes weird things happen. You wait long enough, weird things will happen. But they probably didn't this time. So the most logical conclusion, if you pick 400 people and half of them are left-handed, either something unacceptably weird has happened, which I'm not going to accept, hence the word, or you're going to rethink the idea that 10% of what you were picking from were left-handed, right? Similarly, if you flip a coin 100 times and get something very far away from 45 to 55 heads, you're going to start taking another look at the coin, right? You flip a coin 100 times and get 90 heads. Either it is a very, very, very weird sample, which I don't think, although it could be, or you're going to take another look at the coin, right? So just to look at where we're going with this. In any case, what about the proportion of left-handed people when you pick 400? Well, it's bouncing around 10%, of course. 0.1 is a decimal. P times 1 minus P over N square rooted. 0.1 times 0.9 over 400. 0.1 times 0.9 over 400 is scientific notation, 0.000225. Square root of answer, anyway, is 0.015, which is what I'm getting. Now, reality check. If you multiply this by 400, you will get this. I think that's pretty obvious. And if you divide this by 400, you will get this. Less obviously, if we divide 6 by 400, 6 divided by 400, we're going to get 0.15. And then again, if we multiply this by 400, 0.015 times 400, sure enough, I get 6. So again, multiply or divide by 400 to take the one variable to the other, to take the one mean to the other, to take the one standard deviation to the other. So there are some examples of how the means and standard deviations play out for a binomial random variable. And it looks like I was wrong. I think I'm going to have to go to 3 parts on this video, so I will stop it here-ish, and we'll pick it up around here. But just to give you an idea, we've talked about this before. We talked about it incessantly in sections 5 and 6. It is one thing to be able to compute the mean and standard deviation of a random variable. It is another for them to be useful. Now, we did have a parlor trick with the mean of a random variable, right? It was the long-term average of many repeats, so we could throw it into reverse, right? The average of many rolls of a die is probably around 3.5. So what do 1,000 rolls of the dice add up to? Well, 1,000 times 3.5 per roll. You can work it out. You can reverse engineer it. But it was a parlor trick. It was not of great interest to us. And as for the standard deviation of a random variable, although we've spent a lot of time computing it in section 5 and 6, and here again in section 8, and again coming up in section 9, although we've spent a lot of time computing the standard deviation of a random variable, we've only seen one time when any kind of standard deviation has been useful, and that is in combination with our normal charts. So I'll show you how that plays out next time. Everything that we have been talking about is preparing you for this. This is where the course starts to come together, right? If this is your pattern of randomness, then anything you're talking about involves adding together specific possibilities to amalgamate them. What is the probability of an even number of people with blue eyes? Well, this plus this plus this, right? Adding up individual possibilities. But in scenarios like this, on the one hand, we're not going to be adding up individual bars to find answers. When there's 2,000-ish bars, it's a non-starter, right? But on the other hand, look at it. We know how to deal with this shape. So it's a question of putting it all together. But where do we stand? If something has approximately the normal shape, and we've just got done talking about its mean and standard deviation, then that's all we need to know for those section 3 procedures to kick in. So I'll show you how all that fits together in the third and final part, hopefully, of the section 8 videos.